Hi all, and welcome to Physical Attraction. This episode is based on some articles I wrote on 2D materials such as Graphene for Singularity Hub, which have been modified and enhanced with some additional material. I hope you enjoy. Since graphene was first isolated in 2004, a Nobel Prize-winning feat that sparked a whole new exciting field of material science research, 2D materials have had all kinds of suggested applications. Now, at the cutting edge of research, material scientists are discovering that stacked layers of these atomically thin materials can open up a whole new world of fascinating and useful properties. Graphene's discovery was something of a throwback for physics. It was a far cry from the huge collaborations of LIGO, the first to observe gravitational waves, and CERN, who found the Higgs boson, which require thousands of scientists and billion-dollar equipment. This instead was a genuine story of a few individuals who made a very notable discovery with some basic equipment. Professors Geim and Novoselov, the only individuals to have the honour of winning both a Nobel Prize and an Ig Nobel Prize for the discovery of graphene and levitating a frog with magnets respectively, were responsible. They had special sessions on Friday afternoons which were generally reserved for unusual, weird or off-the-wall experiments. It was in this context that they discovered graphene when experimenting with some sticky tape and a block of graphite. They noticed that the flakes of graphite which could be produced were quite astonishingly thin, and wondered whether it would be possible to create the thinnest possible material. Amazingly, doing this, they were able to exfoliate a single layer that was a single atom thick. When the two scientists won their joint Nobel Prize in Physics in 2010 for their groundbreaking experiments, the Nobel Committee made a point of citing the playfulness that was one of the hallmarks of the way they've worked together. Playing about with sticky tape on a Friday afternoon might sound like a jokey thing to do. Quote, "A playful idea is perfect to start things, but then you need a really good scientific intuition that your playful experiment will lead to something, or it will stay as a joke forever," Novoselov says. Geim levitated a frog in 1997 to showcase his work in magnetism and invented a new kind of sticky tape based on the adhesive feet of gecko lizards, which can walk up walls and hang upside down on ceilings. The original idea of working with graphite was to see if it could be used as a transistor, the fundamental switching device at the heart of computing. In fact, Novoselov says, they had almost given up with graphite when they learned about how microscopy researchers working across the university corridor use Scotch tape to clean the mineral before putting it under the lens. Quote, "It was not a new technique and I'd heard of it before, but when you see it in front of you, it makes it obvious what it can be used for," said Novoselov. Graphene conducts heat better than any other known substance. It acts as a barrier to the smallest atom of gas, helium, and yet allows water vapour to pass through. This particular property has allowed two Russians to perform another playful experiment, this time in passive vodka distillation. Water evaporates through a graphene membrane placed over a mug of watered-down vodka, leaving the concentrated alcohol behind. The inventive step that made Geim and Novoselov into Nobel laureates was to find a way of transferring the ultra-thin flakes of graphene from Scotch tape to a silicon wafer, the material of microprocessors. Once they did this, the extraordinary electrical properties of graphene could be witnessed and explored, including its ghostly quantum state when electrons start to behave weirdly as if these particles have no mass. Quote, "The excitement would exist even without these unusual properties because graphene is the first two-dimensional material. It seems obvious now because we can suspend it in the air and do almost everything with it, but at the beginning it was by no means obvious that it would be stable," Novoselov says. The discovery may have been low-key and unexpected, but the subsequent hype over the properties of this material certainly was not. Graphene is ultra-light, immensely tough, yet flexible and stretchable. Often with excellent electronic properties, 2D materials can be highly conductive of electricity. Some 2D materials can be stacked together or combined to have tunable semiconductor band gaps, which effectively means that the materials can absorb photons of different wavelengths and the electrons can jump between two different states. The band gap is the energy gap that these electrons can be in the different states, which can make them the perfect materials for producing super efficient solar panels, which are tuned exactly to the wavelengths of light from the sun that they need to harness. Although the strength and flexibility of graphene led enthusiasts to imagine using it as a new, omnipresent, and superior construction material, it is these optical and electronic properties that are providing the first use cases for graphene. A recent study blended various types of graphene to develop an LED that could emit light across the entire visible spectrum. Conventional LEDs emit at a single wavelength, and so displays need mixtures of red, blue, and green to produce a full-colour image. If the graphene-based LED could be stabilised and made more efficient, you'd only need one LED with tunable colours, allowing for flexible displays. 2D materials can seem miraculous to the extent that experiments were done to see even if graphene could be made bulletproof. It's not all that far-fetched. Although atomically thin, graphene is very efficient at transferring momentum through its lattice, and bulletproof materials like Kevlar often work by efficiently dissipating the energy from the small area of impact to a much wider area. While it took 300 layers of graphene, with gaps between each layer, to stop a specially designed microbullet, scientists last year discovered that two-layer graphene can undergo a phase transition to become harder and stiffer than diamond. Since its discovery, graphene has been joined by many other 2D materials. Stannine is atomically thin tin. Stacking multiple layers of stannine could result in a phase transition to superconductivity, even though tin in bulk isn't a superconductor. As yet, the transition temperature doesn't put bilayer stannine in the range of high-temperature superconductors, but any new manifestation of superconductivity always has physicists excited for the ways that it can be observed and understood, and can shed new insight into how superconductors work and how electrons correlated together work. Germanium was an element that was initially of interest due to its electronic properties. Many of the earliest transistors used germanium instead of silicon, although until recently it has been supplanted by silicon, which is easier to find in the Earth's crust and to use in mass manufacturing. Now, with the isolation of germanium in 2014, individual layers of germanium are among the 2D materials that are touted alongside graphene. While graphene's famous hexagonal crystal structure is flat, germanium's crystal structure is buckled. Its lattice consists of 2 vertically separated sublattices. External strain, or applying external electric fields to germanium, can cause its bandgap to change. This owes to that double lattice structure that we discussed, but it can also allow germanium to be used in field effect transistors. Not to be outdone, silicon itself has a monolayer counterpart in silicene. The early hype around graphene's applications have been replaced by a more steady approach that is starting to yield more benefits. Sure, we don't have bulletproof graphene planes, trains and automobiles yet, but graphene is slowly and surely moving towards fulfilling its potential as more research into each possible application is conducted. Graphene-based sensors are already being widely produced. Despite all the hype around replacing silicon as the basic material in electronics, some of the first commercial 2D uses of materials like graphene have been in sports gear. In the long term, it seems likely that graphene and other 2D materials will find their niches. In the meantime, the experimental insight that stacking together individual layers of atomically thin materials can result in new, unexpected, and useful properties has opened up a new field of research into van der Waals heterostructures. These materials exist in a transition regime between the bulk properties of large-scale matter that we're familiar with and the quantum realm on an atomic level. The result is tantalizing for theoretical physicists and technology developers alike. These heterostructures are stacks of various layers of graphene, germanium, silicene, and stannine, but also molecular monolayers, so layers atomically thick with different molecules in rather than individual elements. They're named after the weak van der Waals forces that attract molecules to each other. These forces are due to the shifting distributions of charge in the layers of molecules as they interact with each other. These van der Waals forces are weaker than electrostatic forces of repulsion and attraction between electrically charged particles, and they tail off more rapidly with distance, but they're enough to keep these Lego-like structures together. Planes of atoms in hexagonal 2D arrangements can be stacked, and then the possible range of fundamental physical properties and materials to study can be multiplied exponentially. Each newly synthesized 2D material adds more potential combinations, and already layers 13 deep composed of 4 different materials have been synthesized and examined for their properties. Consider, for example, the attention paid to trying to find a high-temperature superconductor. We know that the most desirable material property is subtly linked to the structure of the crystal lattice, as in the case of the yttrium, copper, barium oxide or YCBO structures. Stacking 2D materials offers an exciting new way to probe these phenomena experimentally by trying to create lots and lots of different lattice structures. What if we mimic layered superconductors by using atomic scale Lego? Bismuth, strontium, calcium, copper oxide superconductors, or BSCCO, can be disassembled into individual atomically thin planes. Their reassembly with some intelligently guessed differences seems worth a try, especially when the mechanism of high-temperature superconductivity remains unknown, wrote Professor Geim in Nature. So there's this idea that you can use these building blocks to try and synthesize all sorts of different crystal structures and play around with them, creating things that have never existed in nature before, and see if you can probe into how these fundamental material interactions work, and improve your theoretical understanding of how electrons behave in materials, which is crucial to these things like how superconductivity works. For the moment, graphene remains the most likely 2D material to see near-term applications, partly due to the funding for its research and partly because it can still be produced more swiftly. The exfoliation method of gradually pulling apart layers of graphite to obtain graphene can't be used with every 2D material, even though it produces the purest crystals. Many of the more exotic materials must be produced by something called molecular beam epitaxy, and this is effectively painstakingly depositing individual atoms onto a surface at conditions of high vacuum so that nothing is there to get in the way, and high temperature. And this will limit the mass manufacturing possibilities or the bulk uses for 2D crystals until molecular beam epitaxy gets cheaper, or perhaps more likely given the high temperatures and vacuum needed for MBE, until another manufacturing technique for these things is perfected. Yet it seems inevitable given the demand for ever-improved electronic components for batteries, semiconductors, transistors, and for optoelectronics like solar panels and LEDs, that we will learn how to best exploit the astonishing 2D properties of materials. This is the dream of manufacturing reaching the cutting edge of fine-tuning fundamental physical properties with a careful choice of materials and a careful design on the fundamental atomic level of what you're creating. Like kids with a Lego set, ultimately, maybe the only limit to what we can build is our imagination. Now, graphene is a highly unconventional substance. I mean, after all, how many other Nobel Prize-winning breakthroughs are made by scientists messing around on a Friday night? But since then, graphene and the whole family of additional 2D materials such as germanium and silicene have been a source of fascination and excitement due to all of these fascinating properties that they have that we've discussed. But despite all of the speculation, perhaps the most unusual and exciting property of graphene, which was first isolated back in 2004, took an additional 14 years to discover. Increasingly, as scientists started stacking together layers of 2D materials to create these van der Waals heterostructures, they finally noticed a bizarre and exciting discovery that could occur with graphene, and this is what's called twisted bilayer graphene. So how does this work? Take two layers of graphene, twist them so that they're at a very slight angle to each other, only 1.1 degrees to be precise, so a tiny angle between them, and then stack them together. This is easier said than done. The idea was first proposed in 2007, but only actually realised experimentally in 2018. The resulting bilayer graphene is a superconductor. When the temperature is dropped below a critical threshold, the material has no electrical resistance at all. Layers an atom thick are naturally lightweight, yet also surprisingly tough and flexible, which is what led to the initial speculation for graphene being used as an ideal building material or protective body armour or something along these lines. But it's these electrical properties of graphene which arise from the unique behaviour of electrons in such a thin layer that have led to its first use cases. Superconductivity on top of everything else is the icing on the cake for this remarkable material. Of course, twisted bilayer graphene is not the first substance to experience superconducting properties. We know, for example, that there are, amongst other things, superconductors can generate extremely high magnetic fields without losing energy due to electrical resistance, and these are already widely in use. Some main examples might include superconducting magnets, such as in ITER, the world's largest fusion device, which is currently under construction. Yet there are fascinating unsolved questions in superconductivity, even as it's discovered in more and more different materials and under different conditions. The discovery of unconventional high-temperature superconductors in the 1980s led to speculation that a room-temperature superconductor may one day be discovered. But with no closed physical theory that explains how unconventional high-temperature superconductors work, it's extremely difficult to predict which materials might exhibit this behaviour in the future, as well as to search for better materials which can generate larger magnetic fields, operate at higher temperatures, or turn out to be easier to build with. If discovered, these high-temperature superconductors could enable smaller fusion reactors, or even lossless power transmission, as well as frictionless high-speed transportation. And all of these things could potentially help to solve the energy and climate crisis. But of course, actually understanding how these things work and knowing where to look for these materials that will have these properties has proved difficult. This is where twisted bilayer graphene is most exciting for physicists. It provides a unique way of testing theories of superconductivity. We know that superconductivity occurs in materials with highly correlated electrons. At these low temperatures, with less noise due to random particle motions, the electrons can exert a strong influence over each other, and it's this strong interaction between them, in bulk, that can lead to superconductivity. Unlike unconventional superconductors like YCBO, yttrium barium copper oxide, twisted bilayer graphene has a relatively simple structure. Even producing a crystal of YCBO that will exhibit superconductivity is difficult enough, and the crystals remain poorly understood, what with all the mathematical models that attempt to explain them impossible to solve exactly. To get a YCBO crystal to become superconducting, it's necessary to dope it with impurities that add free electrons to the system, and it's these free electrons and the interaction between them that allows for superconductivity to take place. But these same free electrons can much more easily be added to graphene. The reasoning behind graphene's magic angle arises due to the energy barrier for quantum tunnelling between the two layers of graphene. As you approach the precise angle of rotation, 1.1 degrees, this energy barrier becomes very small, allowing electrons to strongly interact and become correlated between the layers. Part of the reason why graphene and other 2D materials are so fascinating to physicists is that there are known, strange, and interesting solutions to the quantum condensed matter physics of how electrons should behave in a truly 2D or bilayer material that have some fascinating mathematical properties compared to the usual 3D solutions for a bulk material. Finding an actual physical system where these mathematical properties can actually manifest themselves and become real is a little bit like the discovery of black holes, where it was realised that something that may have only ever been a mathematical solution to Einstein's equations of gravity was in actuality a real object with real properties that could be explored to confirm and refine the theory. Now, fabricating this material wasn't easy. It took the lab at MIT that discovered it several years to learn how to produce layers of graphene where the twist angle was this precisely controlled. It was discovered that one of their test devices was a perfect insulator. It didn't allow any electrons to be transmitted. Apply a small voltage, however, adding free electrons to the system, and there was a sudden transition to superconductivity. Once twisted bilayer graphene has been manufactured, its electronic and superconducting properties can be tuned simply by applying electrical fields or pressure to the layers. Twisted bilayer graphene provides a wonderful playground for experiments into superconducting systems because its properties are so easy to tune and change. As Pablo Girillo Herrero, whose MIT lab first discovered twisted bilayer graphene superconductivity in 2018, noted to Quantum magazine, quote, "If there's any system where we can hope to understand strongly correlated electrons, it's this one. Instead of having to grow different crystals, we just turn a voltage knob, or apply more pressure within the stamps, or change the rotation angle." End quote. With this new wealth of experimental data for unconventional superconductors, physicists can get new insight into how strongly correlated electronic materials work. Understanding quantum condensed matter, the properties of electrons in solids, will be key to all manner of future developments, from ever smaller circuitry to more efficient renewable energy sources. It may be possible to find quantum states that can make qubits that aren't so easily destroyed by heat fluctuations, which would help us build the next generation of quantum computers. And of course, the search for room temperature superconductors would know where to look. It's no surprise that, since the initial announcement in 2018, dozens of scientists have flocked into the new research field of twistronics, and of course there's already talk of a Nobel Prize associated with it. Recent research has linked the properties of twisted bilayer graphene to another area of active physics research, the quantum Hall effect. Naturally, experiments are expanding to consider other single atomic layers and investigating the range of material properties that can arise from different twists to different stacks of material. Materials where small twists can dramatically change their optical, electronic, and mechanical properties could, for example, act as semiconductors and therefore be used in computing and telecommunication. Nearly 15 years after it was first discovered, the field of 2D materials that began with graphene continues to hold surprises for physicists. It remains unclear what the most useful and most near-term applications for 2D materials are likely to be as we continue to find and characterise them in more detail and develop faster and cheaper methods of producing more and more complex structures. As we inch closer to a deeper understanding of the weird and wonderful properties of these nanoscale materials, the prospects for applications and devices that exploit the fundamental quantum nature of matter hoves into view. Yet as this surprising discovery demonstrates, there's still an awful lot of fascinating physics at the limits. Thank you for listening to this week's episode of Physical Attraction. Remember, you can find us on the web at physicspodcast.com, where you'll find the contact form. You can get in touch with us there. I always enjoy listening to your emails and reading them. You can follow us on Twitter at physicspod, and Physical Attraction is the Facebook page. Remember, if you want to support the show, there's ways you can do that. There's a PayPal, there's a Patreon, which are both linked to on the website, physicspodcast.com. But the best thing you can do to support us is always to tell other people to listen to the show, especially if there's an episode you particularly enjoyed. Send it their way, and let's expand the range of people who are listening. Okay, until next time then, take care.
Gracias.